discussion or whatever. I mean, I know that, for instance, last lecture I've been a little bit fast. So if you feel a little bit lost, just tell this and we can discuss, right? So where were we on what is Monday? So Monday I discussed the identification of the two notions of Sobolev functions that we discussed. I presented, I've stated Kuvada's lemma, and I showed how this plays a key role in this identification, and also in the identification of the heat flow as gradient flow, both of the Gigli energy and of the relative entropy. Then I did not really prove Kuvada's lemma, but I showed how that statement follows from a statement about Hopf-Flux formula and the Hamilton-Jacobi equation, okay, which is a purely metric statement, not metric measure statement in some sense. And the statement was the following. And this is a statement. So in the general metric setting, this is due to Ambrosio, Savaren, myself, and independently by Goslan, Roberto, and Samson. So there is a little bit of, I mean, the only difference between these two discussions is that they assume the space to be locally compact, but this assumption is in fact easily seen to be, I mean, not relevant. And the theorem tells the following. I mean, I give you a statement, I mean, the same that I gave on Monday, which is sufficient for Kuvada's lemma, although the statement is quite robust and holds, more generally. XD metric. I don't think you need anything. F, say Lipschitz and bounded on X, so from X to R. And let me define QTF. Well, at X, I mean, write this way. So this is the infimum over Y's of this guy, where this is nothing but f of y plus distance squared xy over 2g. So this is the Hopf-Flux formula, if you are on algebra, that's the. Okay. Then say q q0 f equal f. Okay. Then the Lipschitz constant of QTF is bounded by, I guess, something like twice the Lipschitz constant of f, or maybe 4, some constant. Okay, 4 should be 2, but let me put 4. The map that takes T and returns QTF as a map with values, so it takes values on CBX, is absolutely continuous, and is actually Lipschitz. So this space has the sup norm, okay? So Lipschitz means, Lipschitz. Now, in particular, given that, I mean, if I'm Lipschitz with values in the sup norm, for every x, the map that takes x and return, the map that takes t and returns QTF at x is Lipschitz, for trivial reasons. And I can wonder what the derivative is, and the statement is the dt, QTF plus the asymptotic Lipschitz constant squared of QTF divided by 2 at x. This is less or equal than 0 for almost everything. Right? So that's the state. Okay. It's a bit rough. I mean, one can improve a little bit. This statement, for instance, is almost every, in fact, is for every t except a countable number or something like that. But for us, this is sufficient. Right. So in some sense, if here I had equality, this would really tell me that in general, the Hopf-Flux formula produces solutions of the Hamilton-Jacobi equation, right? In some sense, in some metric sense. Okay. Proof. So it is useful to, let me introduce the following two functions, d minus tx and d plus tx. This is the inf of the lim-inf, if you want, of distance x, yn among all yn's minimizing sequences, minimizing for f tx, and this is just the soup of the lim soup, if you want, among all the same way. Okay. So imagine, so what am I saying? Imagine the space is compact, so minima of capital Ftx exists. I could have possibly multiple minima, okay? And d minus is the least distance between x and the minimum, and d plus is the maximal distance between x and the minimum. If I don't have compactness, I don't know if the minima exist, I have to deal with minimizing sequences, okay? So here a couple of trivialities. So first of all, let me bound d plus. I claim that this guy is less than, so claim if you want, this is less or equal than twice t, the ellipsis constant of f, uniform. Okay, and why is that the case? Well, I guess if yn is minimizing, so what it is that so say that yn is minimized, okay, by diagonalization this soup is a max. Okay, so say that yn is a sequence realizing that this the d plus, so I have that f of yn, I have the lim soup, if you want, of fyn plus distance squared xyn over 2t less or equal than f of x, right? And certainly this guy is, of course, is also greater or equal than if you want f of x minus t times the minus the ellipsis constant of f times the distance between x and yn. Okay, lim soup, plus this guy. Okay, so what I get is that what is that I get? I'm getting a little bit messy. So I get the distance squared. So d plus at the end I get this. The dt plus of x squared over 2t is less or equal than the ellipsis constant of f times d plus x, which is this. Does it make sense? This guy, this guy has a limit, this converges to d plus. Okay, so this lim soup, so also this is a limit, if you want, as a limit, because the sum converges to qtf. Okay, so this is a limit, this is a limit. I'm bounding this from below by this guy. Okay, I can play with the lim soup are all limits, so I have no problems in carrying left and right with a minus. I get this, which is this. Make sense? By the way, from now on, given that if I write minimizing sequences, I make a mess in the blackboard, I will cheat and work just in the compact case. Okay, all the proofs are easily adaptable if you replace minima with minimizing sequence without basically any effort. Okay, the only thing that basically you have to observe is that whenever you have a minimizing sequence, if this distance has a limit, then also the function has a limit. And so you can split lim soups and lim-inf, everything is additive. Okay, so that's the first remark. The second claim is the following. The second claim is that f at x minus qtf at x, this is always greater or equal than 0 and less or equal than, I guess, something like 4 times t, the ellipsis constant of f. Okay, for every x. Okay, now this inequality is obvious because in the definition of q, so qt is clearly a decreasing function, right? So because ft, if you let t increase, capital Ft decreases. So if you take the inf of something that is smaller than something else, the inf will be less, right? In particular, here, if you want, you can always pick y equal x here. That's an acceptable competitor. So y equal x, this disappears. You get f of x, no? But qt is the inf, so qt is less or equal than f. Make sense? So this is proved. Now, what about this? Well, we've just proved that this inequality. All right. Now, this means that in fact the qtf at x is the inf, not among all y's on the whole space, but just among all the y's in the ball centered at x and radius, say something a little bit bigger than this, say for instance, I don't know, 4 times or 3 times 4 times t lip f. Make sense of capital F. Actually, let me write this: f of y plus distance squared xy divided by 2t. Make sense? Right? There's no need of going beyond this ball because any minimizing sequence will eventually, be in. Okay. But now, what's the point? Look, just let me let me state it differently. Fix x bar, and notice that what am I proving? No, sorry, I was going to prove something else. Let me think 1 second. Sorry, this is true but irrelevant for this purpose. So let me. So I mean, sorry, this is true but irrelevant. Let me actually observe the following: f of y. So this difference. So qtf at x. So this is. Let me put this way. This is equal to the sup in y of f of x minus f of y minus distance squared xy divided by 2t. All right. Now this is less or equal than the sup over y of the Lipschitz constant of f times the distance between x and y minus distance squared xy over 2t. Right? Okay, but now this is a parabola, right? So the sup over z in R of Lz minus z squared over 2t. This we know what it is. It's something like TL or 2TL, something like this. I mean, we take the derivative, we take the maximum. So whatever is, so you see here, this is super y. This z is the distance between x and y. Right? So this is proved. Okay, some constant is there. Okay. Make sense? Okay. Now actually the other claim, and this was useful for this. So the claim now is that the Lipschitz constant of, I mean, 1 holds. For instance, 1 holds. This. Okay. Why 1 holds? So 1 holds because as I was saying, QTF can be realized not just by taking the inf over the whole space, but just taking the inf over some ball. More generally, for let me put this way. So for fixed, say x bar, if I want to explore, and let me say x belonging to the ball centered in x bar, and with radius, I don't know, something like t times the Lipschitz constant of f. Okay, we have the QTF at x is the inf over y belongs into some ball of radius, some constant, I don't know, 4, 8, some number, t lip f, universal number that I can compute if only I were not lazy. And this is of f of y plus distance squared xy over 2t. Make sense what I'm saying? Right? For any given point, the inf is realized over the ball of radius number times t leap f. Okay. Now, if I let this point vary over a ball of radius t leap f with center at some given ball, in some given point, up to possibly enlarging the number a little bit, this is what happens. Okay. Now, why this is relevant? Because on a ball, look, the function y to distance squared xy over 2t on the ball b constant t leap f centered in x. This is C prime Lipschitz. C prime. So this is what's the Lipschitz constant of this thing? The Lipschitz constant of distance squared at a point is basically distance from the base point. Okay. So here there is a division by t, but I'm looking to the ball of radius t times something. So this should be C prime leap for some C prime. Make sense what I'm saying? Is it true? Yes, it should be true. Okay. Right. So if I scale things correctly, right? So the function. So look at the function. No? I mean, fix x. The function distance squared from x at a certain point y as Lipschitz constant, which is bounded from above by the distance from x. Right? If I divide it by 2t, the Lipschitz constant, local Lipschitz constant, is bounded by distance from x divided by t. Okay. But if my distance from x is bounded by constant t Lipschitz, this t simplifies with the t denominator, and I get. Okay. Now, fx is not a fixed point; is a point which varies over a ball of radius again t times Lipschitz function centered at some point x bar. Okay. So and that's also I can, if I take this big enough, this ball contains b t what it is fix a bar say b2t for instance slip f bar x. Make sense? Okay, and now is the conclusion of the argument. Basically, I'm looking at this function in this ball. Okay, over this ball, this function is obtained by taking infima in y of these functions, but these functions over this ball are uniformly Lipschitz. Right. So on this ball, this function is uniformly Lipschitz. Okay, makes sense. So the inf of a uniformly Lipschitz family of functions is uniformly Lipschitz. Okay, so perhaps this proves something. Let me be more precise. I proved a local Lipschitz regularity. So let me put this way: the asymptotic Lipschitz constant of this is less or equal than, I don't know, some constant Lipschitz of f. Okay. In principle, if I don't know that if I don't know that the space is a length space, or a geodesic space, I don't know whether a local Lipschitz control implies a global Lipschitz control, but still, this. Okay.
Sorry, question.
Please. Yes.
You should have some t in the denominator in these Lipschitz constants. Why don't you?
No, I don't, Vitali. I don't, because of this trick. Because this trick over here. So let me repeat the argument.
Oh, sorry, I get it. Yes. All right.
You see?
Because
I'm looking over a small ball, right?
So there is a t in the radius of the ball. Okay.
Yes. Yes, which can be as small as I wish, as far as I'm interested in the local Lipschitz constant, that is sufficient. Of course, if I'm on a geodesic space, I can integrate the local Lipschitz constant and get a global Lipschitz control. But for now, okay.
Okay, thank you.
Sure. So I proved this. I gave an idea of why this is true. Now, let's actually compute. So let me see. Yeah, let's prove. No, okay. Let's go on now and prove the actual, hot flux formula and the rest of the proof. So, and I need some remark. So clean. The map, x into d minus tx is lower semi-continuous. X to d plus tx is upper semi-continuous. And this is trivial by diagonalization. Okay. If you have, imagine in the compact case, imagine you have, say, let's put the upper semi-continuity. Imagine you have xn converging to x and yn minimizer for f t x yn. Imagine that everything is compact, so imagine that yn is converging to some y, and imagine that yn is a minimizer chosen so that the distance between xn and yn is equal to d plus tx. Well, then it's not hard to prove that if given that the yn are minimizers, everything is compact, everything is continuous, y is a minimizer. For the limit function f t x dot. So yn was a minimizer for xn, okay, and it follows that y is a minimizer for x. But therefore, clearly this guy is converging to distance x, y, because xn converges to x and yn converges to y, and y is a minimizer. Maybe there is another one and where the distance is bigger, but this is a minimizer. Okay, so this proves the upper semi-continuity of d plus, and analogously the lower semi-continuity of d minus follows. Right? Now, interestingly, d plus and d minus are often actually the same function. So the claim now is that d minus tx certainly is less or equal than d plus tx at any x, right? That is obvious. But this is also less or equal than d minus sx, if s is bigger than t. Okay. In particular, d minus tx equal d plus tx for every t except the most accountable number. Okay. Let me prove this. So this is obvious, of course. So let's go improving this. And what it is that I do? Well, I pick, pick, yt minimizer for, capital F t x dot, so that the distance between x and yt equals d plus tx y, d plus t, and also pick ys minimizer for this other guy, so that the distance between x and ys is equal to d minus sx. Right? If the space is locally compact, sufficiently compact, you can do, otherwise pick minimizing sequences. Okay. And now just notice that, given that yt minimizes this, what does it mean? This means that f of yt plus distance squared, but let me write directly dt plus squared, actually, let me write this way. Distance squared x yt divided by 2t. This is better, this does better than what ys does for the same function. This is better than f of ys plus distance squared x ys divided by 2t. Okay. On the other hand, ys also minimizes something. So let me write it. F of ys plus the distance squared x ys divided by 2s. This is less or equal than what yt does here. X yt divided by 2s. Right? You sum this, the functions get away, and you use the fact that 1 over t minus 1 over s is positive to conclude. Okay. So this proves this inequality, and now you have two functions, both are monotone, you see, and they are in some sense one contained in the other in some sense. But you know that the monotone function from R to R must have at most a countable number of discontinuity, right? Because every discontinuity should be a jump. Every jump should contain some rational point, and these rational points, are all different from the other because the jumps are, disjoint. And therefore, at any point of continuity of both these guys agree. Make sense? I think the picture here helps, more than, or perhaps let me. So if t, if t is continuity, let's say for d plus dot x, then what it is that we have? So we have the d minus. So d. Let me see. Okay. Okay, I get the point. From the above, it follows that d plus dx is always less or equal than the limit as s goes to t from above of d minus sx, right? And it's greater or equal than d minus tx. Okay. So if I have a point of continuity for d minus, this guy is equal to this, and this is also equal to dt. And similarly for continuity point of plus. Make sense? Right? So I have these functions that are more increasing. Sometimes they make jumps, and d minus basically stands here, and d plus stands here on the jumps. But on the rest of the points, these are. Make sense? All right. Further claim. The further claim is that the map that takes t and returns qtf at x for any fixed x, this map is locally Lipschitz on the open interval with derivative which is equal to minus, let me write this way, or maybe 2 distance, 2 for almost everything. Okay. I'm not claiming anything about regularity at time t equals 0. In some sense, this is taken care of by an estimate that I erased, I'm afraid. Yes. Well, I wrote an estimate before that now I erased, but that takes into account the regularity at time 0. But now this, this is another computation. Okay. Well, let's compute this. So let's do qsfx minus qtfx. Let me take as before yt minimizer for this and ys minimizer for this. Okay. But if yt minimizes this quantity is less or equal, I pick yt on both sides, for both terms, and this is less or equal than the distance squared yt x divided by 2s minus distance squared yt x divided by 2t. Make sense? Because the function, the f part of yt gets cancelled, right? All right, but this is equal to, you know, this is equal to distance squared x yt times what? Divided 2ts, and here I have t minus s. All right. Well, but that's this. So Lipschitz continuity now follows local Lipschitz continuity because you know, this guy is uniformly bounded, right? By you know, this d plus, now this is bounded by d plus tx, and d plus was bounded by some t like times the Lipschitz constant, something like this. So it's locally uniformly bounded, and this is, you know, as far as S and T are far from zero, this provides a local Lipschitz regularity. Of course, this is a one-sided local Lipschitz regularity, but I can swap S and T here. It is totally symmetric, right? And so what I also get, if I divide it by S minus t and let S go to 0, I get the Delim sup. Sorry, S go to t of this difference quotient. This is less or equal than d plus t x times, you know, times, I guess, minus 1 over 2t squared, right? Make sense? But now is that okay? But I can do the same. I can do the same with bounds from below. Let me show you so that you're convinced that I'm not cheating. So this gives a bound from above. For the bound from below, I start observing that QSF minus QTX fx. This is greater or equal. Now I pick ys in some sense. This is greater or equal than distance squared ysx divided by 2s minus distance squared ysx divided by 2t, right? And this is distance squared xys times the same thing as before, t minus s divided 2ts. So if I divide it once again by s minus t and let you know, as s goes to, actually I could pick s goes to t, do the limit, this difference quotient is greater or equal than again the same quantity as before, actually, of you know, when s goes to t, ys, so this quantity is greater or equal than d minus sx, but then I use the lower semi-continuity of d minus, and then I get d minus t x squared times minus. Okay. And then if I divide by s minus t with s smaller than t, I get the other inequalities. Okay. Does it make sense what I'm saying? Here, notice that I use the semi-continuity of d minus even in t, which follows by the same arguments that I used before. I showed the semi-continuity in x, but this is in x and t. Does it make sense what I'm saying? All right. So this is proved. Right. Okay, now to conclude the proof, or almost conclude the proof, let me just notice that. So I computed the time derivative of qt. Is given by this distance function, basically. And so now the claim. Is that the asymptotic Lipschitz constant of QTF at x, this is bounded from above by dt plus x divided by t. And you see that if I prove this, I prove this inequality, right? Because this derivative is equal to d squared over 2t squared. But Lipschitz constant squared divided by 2 is less or equal than this quantity. So this proves this. All right. And well, let's compute it. So let me pick z and y, if you wish. Actually, let me say x1 and x2 close to x. Okay. And let me pick, say, y2 minimizer for this. And so this is bounded from above by the same trick. This is always the same formula. Distance squared y2 xo y2 argmin of ft x2. So divided by 2t. This is x1 minus distance squared y2 x2 divided by 2t. By the usual, y2 is optimal linear, it's possibly not optimal linear, so I get a bound from above. Now let me continue. This is less or equal than, a squared minus b squared, difference of squares. This is bounded from above by, let me say distance x1. Let me do all the steps. Y2 x1 minus distance y2 x2 times distance y2 x1 plus distance y2 x2 divided by 2t. This is equal. Actually, this is equal. I've done nothing. But now this difference by the triangle inequality, this is bounded from above by the distance between x1 and x2. Right? And what about here? So this is bounded from above. So let me write. So this is bounded from above by the distance between x1 and x2 again, plus the distance between y2 and x2. Right? So this is bounded by, let me write it here, twice d plus t of x2 plus the distance between x2 and x1 divided by 2t. Right? Because this guy, of course, is less or equal than d plus x. Right? By y2 is a minimized. All right. Now divide by this quantity and take the lim sup as x1 and x2 go to x. So you think the lim sup as x1 and x2 both go to x of qtf x1 minus qtf of x2 divided by the distance x1 x2. This is less or equal than what? So this I divided, this goes to 0. This I use the upper semi-continuity of d plus. This is less or equal than dt plus of x divided by t. But now this expression is totally symmetric in x1 and x2. So I can take, if I take the absolute value here, or if you wish, if I replace x1 and x2, I swap them, get an inequality for the absolute value. Make sense? So I proved my claim, right? This is the asymptotically constant. This lim sup. Okay. All right. Very well. So what happened? We are done. It's just now a matter so this is proved, as I mentioned, because I compute exactly the derivative, and then I show that derivative is bounds from above this asymptotically constant. So this is proved. Right? The only thing that remains to be proven is the Lipschitz regularity of the function with values in CB. Okay, then the problem is that I can have issues at time t equals 0 because my estimates typically tend to blow up in principle. But I'm saved by this equation. Now that I know what is the derivative, I'm saved by that equation because if you want, or if you wish, by this, because I know this is telling me, if you want, look at this, that the model for any x, this is equal to d, well, sorry, tx divided by 2t squared, right? But we know that this guy is bounded from above by what was some constant times t, the Lipschitz function of f. So this is less or equal than some universal constant times the Lipschitz squared of f. Right? And now I'm done because so this is telling me that for any x, the caret xt and the trans qtf of x, in fact, not only is locally Lipschitz in here, but in fact, I mean, it extends the Lipschitz regularity up to 0. It has the uniform up to 0. You see what I mean? The derivative is uniformly bounded. And also uniform in x. Right? And so we are done now. This tells us the desired uniformity is given, right? How much is the difference between, say, f and qt of f at some point? Well, it's at most t times, this for any point. So the estimate is uniform. Okay. So end of the proof. Okay. Yeah, I guess this could be, if there are no questions, this could be a good moment to take a break. 5 minutes, and then we resume. And we completely change topic. All right. No, not yet. Ok, va bene. Aspetta. No, non c'è problema. No, ok. All right. It's a good time now to stop for a second and wonder a little bit what we have proved so far, and basically what we have learned so far about CDK infinity spaces. And I would say, I mean, we can summarize what I've done during this course, but in this bullet points. So first of all, on arbitrary metric measure spaces, no need of a CDK infinity assumption, Sobolev functions can be defined either by relaxation or via weak upper gradients, and the two approaches coincide. Okay, one speaks the L2 language, the other speaks the W2 language, but they, in an arbitrary metric measure space, they give the same result. Second, and here CD is crucial, there is a well-defined and stable with respect to measure Gromov-Hausdorff convergence notion of heat flow. And the heat flow satisfies in a natural way a sort of heat equation. I mean, we wrote this. Okay, solutions of the heat flow satisfy this. Here, stability comes once again from optimal transport point of view, much like the CDK infinity condition is stable thanks to the optimal transport approach at Ostrom-Bidani. And while the equation, the PDE, comes from the more Sobolev point of view. So again, there is this interplay between Wasserstein and Lebesgue geometry, if you wish. And this heat flow can be seen as gradient flow in two a priori extremely different, but in fact equivalent in a very abstract framework sense. Okay. Lastly, we have learned that the heat flow in general is not linear. Okay. And this is not linear because there is no need for our. This is totally invisible from the Wasserstein point of view. By the way, you will never see linearity of the heat flow by looking at the gradient flow of the entropy. Once I heard Jan Brenier making the following joke: there is an alien civilization that studies the heat flow at the beginning, not as gradient flow of the Dirichlet energy, but as gradient flow of the entropy in the Wasserstein world. And then some mathematician in alien space proves that the heat flow is linear, and of course he wins the Fields medal, right? Because there's absolutely no reason at all, if you look at the Wasserstein point of view, to realize that the heat equation is actually linear. Okay, if you look at the Lebesgue point of view, that is evident, and is evidently linked to the fact that the Cheeger energy is a quadratic function. Okay, or if you wish, to the fact that W12 is Hilbert space. Okay, this of course is the infinite dimensional analog of if I have a smooth function over Rb. If you take its gradient is linear if and only if the functional is a quadratic form. Okay, that's equivalent. All right. Okay. Now we know by experience that typically having a linear Laplacian is a good thing. Okay, so perhaps it could be a good idea to have a look to the spaces where the Laplacian is linear. Okay, and our chances of actually, in fact, I could, give now the definition and say, okay, a space is a linear CD, infinity space if the Laplacian is linear. Okay, and by the stability property, in some sense, that for free, I mean after all the work we've done so far, prove the stability of this class of spaces. But now the question is, okay, what do I do with this class? So how can I, handle, geometry or analyzing this space? What do I actually earn, from the assumption of linearity of the Laplacian? So in order to make any concrete use of this assumption, we need that I'm going to make maybe Monday or next Friday, is we need to sharpen our calculus tools. Okay, so far, our best understanding of the Laplacian is sitting in the weak integration by parts formula. Right? This we know, but this is clearly, in some sense, does not really see any. I cannot really use the linearity of the Laplacian in here to get anything interesting. Okay. In some sense, what I want to do today is to improve this into I really want to integrate by parts. So my next goal is to understand this, okay, and perhaps understand this right-hand side. Okay, and because of this, it's better to take a step back and have a look to the standard, or perhaps not standard, but the smooth Fiedler case. And so this gives us will give us an idea on how to define this object in purely metric measure spaces. So let's say we have a Fiedler manifold, or in fact everything here lives on the tangent and cotangent space. So let's just pick RD with a no. This no may or may not come from a scalar product, I don't know. Okay, and take F from this space into R smooth. Then who is the differential of F at some point? Well, this is is well defined regardless of the norm. This is you can define it, for instance, as this is the element. Let me put this way. Let me be precise. This is the element of the dual of this guy, which of course I should think as the dual over D, because RD and the tangent at X is RD, they're all the same. It identified, given by dfx applied to a certain vector v is the limit as epsilon goes to 0, or as t goes to 0, of f at x plus tv minus f at x divided by t. The norm has no role in it. Okay. Now, who's the gradient? Now, here the metric comes into play. Okay. The differential is something living in the cotangent space. The gradient is something that lives in the tangent space and is related to the differential. Okay, and it comes from a you have seen this in Banach space theory for sure. So whenever you have a Banach space, right, you have the dual, and the every vector, for every, let me write it. So for every, say, v in the Banach space that exists, possibly not unique, L in V star, such that L of V is equal to the norm of V squared, and the norm of L is the same as the norm of V, right? You see that that's the guy or one of the guys realizing the norm of V. Okay, this L in general is not unique, and this possibly multi-valued map that takes V and returns this set of L's is in fact a single-valued and linear if and only if V is an Hilbert space. In which case, this is nothing but the Ritz isomorphism. Okay. Now we can do the same. In fact, this is the same. Notice that this. I mean, it is convenient to encode both of these in the same inequality. Notice that actually, let me write it. So this is the same as saying that L of V is greater or equal than 1/2 norm of V squared plus 1/2 norm of L star squared. No? Notice that this inequality always holds. No? If you have an element V of a Banach space, an element of dual, by definition of dual norm and Young inequality, this inequality is always true. Right? So if the opposite holds, I'm really encoding both of these. You see? Makes sense? If you want, this is the same argument that we used when we introduced the George's notion of metric gradient flow. Right? So this was the starting observation. Okay. All right. So coming back on our Fiedler setting, so grad f at x, see? Now, in general, this is not a single value guy. This is the set of now V is a guy in the tangent. So this is in Tx Rd, which is Rd, such that the differential of f at V is greater or equal than 1/2 the norm of the differential squared at x, I would say, plus 1/2 the norm of the squared. Rd was coming with a norm, so Rd star as a norm, the dual norm. It is the norm that I'm using to, in here to compute this differential. And I'm saying, that now V is a gradient if, the same idea, except that I'm sort of swapping tangent and cotangent. Okay. Notice that this is always non-empty and convex. I mean, for any fixed x, this is a convex set. Okay. Make sense? Let me try to convince you with an example that in general gradients are not uniquely defined. And I guess that the example we have already seen So take the L infinity norm on R2 and take f of x1, x2 to be equal to x1. Okay? So this function increases when you go to the right. Okay. But given that I'm taking the L infinity norm, now I wonder who is the gradient of this function. Of course, the first guess is, say at 0, the gradient should be the vector, pointing to the right. That's another choice of gradient. But then, because I just have to go to the right. But on the other hand, say the vector 1, 1. This has the same norm as this. And the derivative of the function along this vector is the same as this. So why not? Or why not this? In general, grad f is equal to, in this case is equal to what it is, the set of vectors of the form 1/2 with alpha, less than 1. Okay, you can check that this is the case. Okay, and this should be, that should explain why we don't expect uniqueness. All right. Now, so we were going. So my goal is to understand, at least in the Fiedler setting, what is the differential of G grad f. Okay. Now, if grad f is not single valued, this is not a single valued thing. So the best I can do, is to define, so this would be a multi-valued map, and I could define d plus of G grad f and d minus G grad f, at a point x. This would be the sup among dv in grad fx of the differential of G at x applied to V. And this is, of course, the inf of the same expression. Now, let me perhaps point out that if you open a book on physical geometry, typically you don't see this sort of discussion because typically it is assumed, some smoothness assumption on the norm is imposed. In particular, the norm is typically taken uniformly, at least, well, typically uniformly convex and uniformly smooth, but in particular, typically the norm is taken strictly convex. And if the norm is strictly convex, this guy is a singleton. Exercise. if this norm is strictly convex, then grad f(x) is a singleton. I mean, it's really an easy exercise. So just sit down and think about the statement and the definition of gradient, and you're done. Okay. So in sense, it's a little bit of a warning. You will not find this, but in the non-smooth setting, R2 with the infinity norm is certainly a metric measure space, so it is something we have to deal with. So let's be prepared. Okay. Now here is a relevant observation. That can be seen as yet again one observation linking, if you want, the analysis in the independent variable with analysis in the dependent variable, or L2 and W2 word, or Eulerian and Lagrangian point of view. Remark. D plus F, D plus G, grad F is the limit as epsilon goes to 0 of the norm of the differential of and D minus is the same as the limit as epsilon goes to 0 from below. Let's discuss a little bit what I just wrote. First of all, notice that the map that takes F and returns the differential of F, say at some point X, the norm, I should say, this is convex, right? At any given point, right? Is convex, non-negative, so also this is convex. Or if you want, the map that takes F and does the differential at some point is linear. I post-compose this linear function with the convex function 1/2 norm squared. So this is convex. Any convex function admits directional derivatives. Right? So given that this is convex, for any G, for any, if you want, F and G, if I take the limit, so this limit from the left, from the from above and from below, this limit exists. This limit exists because this lim, for instance, this lim as epsilon goes to 0. This is the same as the inf over positive epsilon, and this is the same as the sup over negative epsilon. Does it make sense what I'm saying? Right? I'm just saying, look, I have a convex function, fix F and G, and look at the graph of the convex. So if you want this map, I put this way. So the map that takes epsilon and returns 1/2 differential of F plus epsilon G squared at X. This is convex. Let me draw its graph. And the graph could be something like, I don't know, should be like this, for instance. I don't know. I have no idea what the graph looks like. I know that this is convex. And now I look at this derivative in 0, the right derivative and the left derivative in 0. The left derivative is this expression over here, and the right derivative is this expression over here. They both exist because the difference quotients, here you see, as far as epsilon goes to 0 from above, the difference quotient decreases. So this lim exists because it's an inf. And as epsilon goes to 0 from below, the limit from below exists because it's the same of a sup. Make sense? Okay. So at least the right-hand side are well defined. Now let me prove that equality holds in there. And you see here, I'm perturbing in the dependent variable, where when I'm computing this, or when I'm computing the differential of G along V, I'm perturbing in the independent variable. So this is horizontal derivation, this is vertical derivation. Well, I mean, let me actually prove. So let me notice the following. So I have the inequality. So pick V in grad F at some point. Then what I know certainly that the differential of F applied to V is greater or equal than 1/2 this norm squared. I mean, everything is evaluated at X, but let me avoid writing this. This is by definition of gradient. On the other hand, I can differentiate the function f plus epsilon g at B, and here I know that this is an arbitrary function, an arbitrary vector. I know that there is an inequality. Please.
For the B plus and the B minus.
Yeah.
There's no reason why they could both be like ints, or they could both be superscript, or am I misunderstanding something?
No, take yes. So yeah, it's simple. It's simple. Take f from R to R convex. Then the lim, say as epsilon goes to 0 of f x plus, I don't know, epsilon minus f of x divided by epsilon. What I'm saying is that the right derivative is equal to the inf over epsilon positive of the same expression. You agree? Actually, let me put it this way. So the map, this map is monotone. This is non-decreasing, increasing.
Okay.
Maybe not strictly, but increasing.
Okay, yeah.
Okay. So now you see, if I don't know whether it is single value that's 0 in some sense, but I can take the inf on positive or the sup over negative.
Okay.
Okay. Other questions? Yeah, don't feel afraid to ask. Now what do? I take the difference of these two expressions, and certainly what I get, the differential here is linear, and what I get is that epsilon the differential of G applied at V is less or equal than the differential of F, this norm square disappears, minus the differential of F square divided by 2. This is true for every F, G, epsilon, and V gradient of F. Okay? Now, if epsilon is positive, I can divide by epsilon, I let epsilon go to 0, and what I prove is this inequality. You see? Because I bounded from above the differential of G applied to V for any V in the gradient. Okay? And if epsilon is negative, when I divide by epsilon, I get the other inequality. So when I get the epsilon, I get this. Okay? All right? Exercise, prove equality. Hint, use compactness. Okay? So that's in the smooth Fiedler setting. Now let's see how we can translate this knowledge to the non-smooth setting. Well, first of all, okay, perhaps here is before erasing this. Here is a starting observation. In principle, in the non-smooth setting, I might be in trouble in defining what a differential or a gradient is. So I might be in trouble in, a priori defining these objects in order to define this. But these things are easier to, I have a notion of norm of the differential. That's the minimum weak upper gradient. So the first thing that I will do is I will take, this right-hand side in some sense as definitions for d plus g, d minus g applied to grad f, even in a setting where I don't know what dg is or grad f is, but, just as a formal expression, and that should, be related to integration by parts in some sense. Make sense? So that's the first thing. And okay, that should be related to, what is the differential of g in the direction of grad f, even though for the moment I don't know what the differential of g is, I don't know what grad f is. So now, metric measure spaces. And the starting observation is, so now xdn. Now take f and g Sobolev. Actually, let me consider them up. That takes Sobolev function z and returns 1/2 minimal weak upper squared of f in L1. This is a function in L1, xm if you wish. This map is convex. Is M almost everywhere convex in some sense. Meaning that whenever you write the the convexity inequality, the convexity inequality holds. The right hand side doesn't have a number, have a function, but the right hand sides, I have the correct inequality almost everywhere. Make sense what I'm saying? Let me write it actually, so that it's clear what I mean. So what is 1 minus t f plus tg squared? This is less or equal than 1 minus t differential of f squared plus t over 2 differential of g squared m almost everywhere. Should be this, right? So it's convex in this sense. This inequality holds. Okay. Now, if this inequality holds by the same argument basically written over here, but rather than for R valued function for L1 valued function, the limit as epsilon goes to 0 of df plus epsilon g squared minus df squared divided by 2 epsilon, this exists both in L1 and almost everywhere. Right? And I call it d plus g nab life. And of course, the lim as epsilon goes to 0 of the same expression by definition will be d minus g nab life. That makes sense? All right. So this sequence, let me perhaps argue a little bit more about what this limit exists. When epsilon decreases, this expression decreases almost everywhere. So we have a decreasing sequence of functions. Okay. But you can check that they're all bounded from below they're uniformly bounded from below by well, for instance, by the value of this expression for some epsilon negative. Make sense? If you put it in the other way, the map that takes epsilon and returns this with values in L1 is increasing. All right. So when you let epsilon go to 0 from from above, it is uniformly bounded from below by the value at epsilon equal 1, and uniformly bounded from below by the value at epsilon equal -1. And plus, I have convergence almost everywhere, so I have convergence both in L1 and almost everywhere. Make sense? Here, if I wanted to write here inf over epsilon, over positive epsilon, I should be a little bit careful in writing that inf is the essential infimum. So if you have familiarity with the concept of essential infimum, that's what you should put here. You should put it here. If you don't have familiarity, forget what I just said. Okay. All right. Now notice that by the monotonicity in epsilon of this, the notation stands. So at least this is less or equal than this. I'm almost there. at least. Okay. Okay. Now, the question I want to address is, do these expressions have anything to do with the concept of differentiating G in the direction of grad f? Right. So that's the next question. So here I used, in some sense, the trick, if you want, of taking those right-hand side as definitions. But now I want to sometimes try to reestablish the equality between the left and right-hand side. But of course, I need some concept of, gradient of f. And in fact, there is such a concept. Without going into the theory of modules that maybe some of you already seen in the recent talks that I gave. And the starting observation is this. Let f be Sobolev and pi be test. Then we know for every t positive, this integral is less or equal. Sorry, no G. Right? This is true for every t, between 0 and 1. Right? For t equal 1, that's part of the definition. For t smaller than 1, what I do, I apply, the definition of Sobolev function to the restricted one, which is still test. Okay. So now this right-hand side, this is certainly less or equal. Let me apply Young inequality. This is less or equal than 1/2 plus 1/2 the double integral. Right? Let me divide by t. And let me take the lim sup. And what I get is that the lim sup as t goes to 0 of the integral of f gamma t minus f gamma 0 divided by t in d pi of gamma, of course. This is bounded by what? Okay, let's have a look. Let's have a look at this expression. Let me use Fubini to exchange the integrals. This is basically this guy. Let me write in green. So this guy is equal to the double integral, so the average integral from 0 to t of the integral of df squared in, with respect to the measure, let me write it away, rho s dm ds, where rho s is the density of es pushover pi. Makes sense? By the change of variable formula. No? This would be like integrating, this is gamma s. So when I integrate something with respect to gamma s, is the same as integrating the function d es pushover pi. Pi is test, so the marginals are uniformly bounded in L infinity. So in particular, Dave density. Okay. Now, what happens to these densities when s goes to 0? When s goes to 0, the measures rho sm converge weakly to rho 0m, in the sense of measures. This follows from the fact, well, perhaps, let me do that here. Let me notice. So notice that, so the first claim is that es pushover pi goes weakly to E0 pushover pi. And why is this true? Because pi is concentrated on continuous curves. What does this mean? This means that what I claim is that the integral of phi composition Es d pi goes to the integral of phi composition E0 d pi for every phi continuous and bounded on X. Right? But this is trivially true if phi is continuous and bounded, because the integrand is uniformly bounded, And point-wise, phi in gamma s goes to phi in gamma 0 because phi is continuous. So dominated convergence gives. So this is true as soon as pi is concentrated on continuous curves. But moreover, given that it is test, these have densities that are uniformly bounded in L infinity. And now it's an exercise to check that if I have a uniformly bounded sequence in L infinity that is converging weakly in the sense of measures, it also converges weakly star, so in duality with L1. Okay, if you want to apply Egorov. Okay. So this to say that this integral has a limit when s goes to 0, when t goes to 0, so that this goes to the integral of df squared, if you want gamma naught, d pi of gamma. So I have a limit here. I have no idea whether I do have a limit in here or not, so let me put a lim sup. 1/2 lim sup as t goes to 0 of this, kinetic energy, if you wish, average the kinetic energy. Okay. So this inequality is an inequality that is always true. Whenever I pick, you should think of this like this. Whenever I pick a function f, Sobolev, and I try to differentiate in the direction of any given test plan, what I obtain is something that is bounded from above, but is continuous. And you should compare this. You should compare this to the expression that we have seen in the smooth world, that the differential of f applied to v is less or equal than 1/2 norm of the differential squared plus 1/2 norm of v squared. It's the same thing, right? Same. It's imitated. Okay. But in the Fiedler setting, what it is that we have done, as soon as we realized that this is always true, we said that v was a gradient if the other inequality holds. So I do the same. Definition. So f is Sobolev, pi is test. I say that pi represents the gradient of f if the other inequality holds. And here I still keep the lim sup. It's a definition. It's just, I'm imitating what I've done in the smooth Fiedler setting. Okay. Well, if you want now, the theorem is this, and this will be crucial. This will be crucial when better studying the heat flow in the non-smooth setting, even in order to get Laplacian comparison estimates, and this is crucial really to make computations in symmetric measure spaces. It has a trivial proof, but it is crucial. And this theorem, as much as all the discussion that I'm making now, comes from my paper on the differential structure of metric measure spaces, Memoirs 2009. Parts of this has also appeared in earlier papers with Luigi and Giuseppe, but then this discussion comes from here. The theorem is this. Say you have two Sobolev functions, and say that pi represents the gradient of f. Okay, so that inequality holds. And now, so pi, since that pi is defined in terms of what happens when you differentiate f along pi. Now try to differentiate g along pi. We can look at the integral of g gamma t minus g gamma naught divided by t d pi of gamma. Okay, let me write it twice. I would like to look at the limit of this expression as t goes to 0. I don't know if the limit exists, so I can only get LMinf, which is, of course, less or equal than the lim sup. So far, I did nothing. Now, the interesting thing is that this is bounded from above by the integral of d plus g nabla f gamma naught d pi, and bounded from below by the integral of d minus g. Right? So, and you see that this is really an analog of what I just erased over there. So this is the horizontal derivative. I differentiate g in the direction of pi, and here is something where test plans don't appear at all, just minimal weak upper limits. Okay? Proof. And the proof is as trivial as the one that I just showed you before in the smooth setting. In the linear case, is this one. Right? What I know that the limit of the integral of f gamma t minus f gamma naught divided by t d pi is greater or equal than 1/2 the integral of df squared gamma naught d pi plus 1/2 the lim sup of the kinetic energy. Let me, okay. On the other hand, by the remark, by the inequality that is always true, I know that if I apply, if I take the Sobolev function f plus epsilon g and apply to this function, I applied what I know for every Sobolev function and every test plan. This is less or equal than 1/2 the minimum weak upper grade of f plus epsilon g plus the kinetic energy. Right? And then, as before, I take this and I subtract this. When I subtract the inequality, since that's going the correct direction, the kinetic energy part drops away, and what I get is that the lim sup of epsilon, the integral of g gamma t minus g gamma naught divided by t d pi. This is less or equal than, actually, let me write this way, the integral of minimal weak upper grade of f plus epsilon g squared minus df squared divided by 2 d pi in gamma naught d pi. Right? Then, as before, if epsilon is positive, so this is true for every f, g, and epsilon, as soon as pi is a test plan that represents the gradient. In particular, it's valid for every epsilon. So if epsilon is positive, I can divide by epsilon, and when I get that this lim sup, which is what I'm interested to bound from above, is less or equal than this expression divided by epsilon for every epsilon. Right? And so I let epsilon go to 0. I use the L1 convergence of this expression to this, and then that. Right? If epsilon is negative, when I divide, I get the other inequality. All right? End of the proof. Now, let me just, I know that my time is over, but let me just give a definition and a statement so that you know where we are going to go next lecture on Monday. Sorry, it's not 2009. I think it's more 2012. 2009 is the first paper on the heat flow. So the definition is this. Same paper. We say that X is infinitesimal Hilbertian if W12 is Hilbert. Okay. So the idea behind this definition is, well, I mean, what we discussed, right? So this typically is Banach, but being Hilbert should be related to some Hilbert property of the Sobolev functions, and should be related to the linearity of the Laplacian, which is something that we would like. Now here is the theorem that I just state, but I want to, just to show you how calculus works on infinitesimal Hilbertian spaces. And the statement is the following. Let X be infinitesimal Hilbertian. Then a few interesting things happen. Then, so D plus G nabla F is equal to D minus G nabla F for every F and G, almost everywhere for every F and G. And the map sending, so let me call this guy DFDG. And the map that takes F, G, and returns this DFDG is bilinear, symmetric, and satisfies the following. So I want to tell you that now, I have the right of calling this DFDG because of the following properties. So I have a Cauchy-Schwarz inequality. I have a chain rule. So if I see one in Lipschitz, and I have the Leibniz rule. Plus, the other guy, F2 D1 DG. Here, F1 and F2 should be also bounded. And Sobolev. And what else? Okay, yes, and if F has a Laplacian and G is Sobolev, then I have the integration by parts G Laplacian FDM. This is actually equal to minus DFDG. Right. So this is the improvement in some sense of the integration by parts formula that I was hinting before. I don't have a less or equal now. Now I really have an equality. And this is really what it should be. And this expression is bilinear. Okay. If you want, it is clear that this expression on the left-hand side is linear in G. Because just introduce it. In general, it's not linear in F because the Laplacian is not linear. But once I know this bilinearity and symmetry of this, then I get this. Okay. So in some sense, this theorem tells us that for what concerns the first order, you can take this way. So for what concerns the first order calculus on infinitesimal Hilbertian spaces, it really looks like a calculus on Riemannian manifold for Sobolev functions. Okay. Let me just conclude with a comment. So one consequence of that statement is that in particular, if I look at this theorem of horizontal and vertical derivatives on infinitesimal Hilbertian spaces, what I deduce is that the limit as t goes to 0 of the integral of g gamma t minus g gamma naught divided by t in d pi, this is equal, because bounded from above and below by two things that are the same. Okay. So this derivative exists, which is incredible, right? So we are taking the derivative. right? A directional derivative, and we are able to prove that this derivative exists. Okay, this is really, one of the cornerstones of the theory from now on. Okay, let me perhaps comment. I will conclude the following comment. There is something which is miraculous on the fact that this expression is symmetric. And if you pause for a second and wonder, even in the smooth setting, this is something that is not really obvious. So take two functions, smooth functions, f and g, a point, and take, you have f, you have g, and now you differentiate f in the direction of grad g, and you get a number. And then you do something completely different, namely you differentiate g in the direction of grad f. These two are the same, okay? Because in both cases it's grad f, grad g. And the reason they are the same has to do with the fact that you are working on a Hilbert space. If you try to do this on a filter setting, this is not the case, because one expression is linear in f, the other expression is linear in g, but in general it is not bilinear, so they cannot be equal, or, they cannot be equal. But if you are on a Riemannian manifold, then they are the same, and this is, in some sense, the counterpart in the metric measure setting of this identity. This right-hand side is symmetric in f and g. Even if the left-hand side does absolutely not look like that. I'm taking g and differentiating the direction of grad f. Okay. Okay, perhaps I did not mention, I gave a definition of plan representing gradients. I did not state any existent results. Of course, if there were no such plans, the theory would be quite empty. In fact, there are such plans, but I'm not proving a general statement because in some sense we'll be interested in basically just one particular case of such plan representing gradients, the one coming from optimal transport. But I will discuss this later on. So I will not care about really a plan representing gradient for arbitrary sublet function, but just for Cantor-Lewis potentials, where optimal transport and CD condition will give us the result. Okay, so for today that's all, and we will resume on Monday, I guess. Goodbye to the line audience. Ciao, Italia.